hydrogen device. Full propeller, the function again is converting torsional energy into thrust, pushing the ship. And the blade of the propeller slice the water and impart the backward thrust, pushing down. Yes. Wind blower and same as you can see the size of the propeller carrying to the human body. Right? If you say that 2 meters, may say 8 meters, 10 meters or diameter, big one. And also the propeller, number of propeller is many, right? 6 of them. How many for the propeller blade for airplane? Can you remember? Airplane. You don't see propeller for airplane nowadays. Most of them are jet plane. There are still a small size of propeller airplane, right? Is 2 blade. There are sometimes 3 blade air propeller. 선풍기가 영어로 뭐냐? Wind blow in the house usually have a 3 blade, right? But this one is many. This one is many. Comparing to the usual ship, it also does not have such many. But this one is depending on the pressure or power delivery. You need to have a more blade. Also, this one shows a skew. Skew is very special, especially for the Navy ships. Skew is known to be less noisy because of the skew. Then you may say that efficiency may be lower compared to the no skew. And this is a blade cut sectional shape of the blade in the middle. And then water is pushed in this way, cutting down angle of attack or other thing. Type of screw propellers. Solid fixed pitch. This is a normal conventional propeller. You don't see such a one here. Oh, this one is fixed pitch. So here's a conventional one. Fixed means no pitch. Pitch is the angle of attack. Angle of attack pitch can be adjusted by rotating this blade. So angle of attack can be changed. So it's control pitch profile. You need to have some kind of controlling devices by switch electrical way of rotating this one, and motors also, right? So that depending on the speed of the ship or power of the engine, you can control the pitch. Nowadays, the wind power system, they also have a controlling system inside. Because the wind blowing is fluctuating. They change not only direction, but also the speed is changed. So they want to optimize the output of the wind, so they control the supercavitating. I already explained that cavitating, the full cavitation is supercavitating. It is also for very high speed. And counter-rotating, there is 2 propellers, two propellers rotating this counter in the other direction to increase the energy efficiency. There's many ideas. Energy control rotating propeller.
Massive ships are powered by massive propellers. Likewise, small boats are powered by small propellers, but the principles are the same. One propeller is the controllable or variable pitch propeller, but how exactly does it work? This vessel is the Hermes. She's an old design deep sea salvage tug fitted with two propellers. I don't know what her original propulsion was, but I can use her for this demonstration and give her one controllable pitch propeller and one fixed pitch propeller. When they're spinning away like this, it's hard to see anything much, so let's slow it down and look at the controllable pitch. Like this, she's running ahead. The propeller blade is cutting the water and propelling it backwards. This is no different to a fixed propeller. When running ahead, they look exactly the same. The difference comes when we want to reduce the speed. To reduce the speed of a fixed propeller, you have to slow the rotation. Very easy if you've either got a gearbox or an engine that can easily vary its speed. It's a bit harder when your engine likes to run at a constant speed. A controllable pitch propeller, on the other hand, runs at a constant rotational speed. To reduce the vessel's speed, you change the angle of attack of each blade instead. It's hard to see while rotating, so let's stop it and have a closer look. Running ahead, you can see it's got a steep angle of attack. This makes it harder to turn, but generates more thrust. As you reduce the angle of attack, the engine has an easier time turning the propeller, but it generates less thrust, slowing the vessel. You can generate zero thrust by setting the pitch to zero. For example, this setting would be used when a ship has started her engines but is still alongside her berth, not yet wanting to move. By contrast, to set a fixed pitch propeller to generate zero thrust, you literally stop it. For a stern propulsion, a fixed pitch propeller needs to turn in the opposite direction. Ships do this either through a gearbox arrangement or sometimes by literally stopping the engine and restarting it in the other direction. The controllable pitch propeller just needs to alter its pitch to be pointing the other way. If we stop it again, you can see the alteration becomes a lot clearer. A shallow angle generates lesser stern thrust, but you can increase it by altering the blades even further. One thing to just compare quickly is the path that the water is directed down. Going astern, you can see the shape of the blade is less efficient than it was when going ahead. This is why ships' astern power is sometimes up to 50% less.
CPP is working. Engine. Another control rotating propeller fan or not propeller. Cavitation. Cavitation and erosion. So, in some speed, speed is high, then the pressure at the surface of blade is low somehow. Maybe behind is low, right? When water comes boiling, because of the pressure is low, water is boiling in low pressure earlier than 100 degree. So, and then the propeller is rotating, so the pressure is not the same as when the blade is here and here. The pressure is fluctuating, changing, so that the cavity is formed and disappeared and formed and disappeared. So that is the problem. When they are collapsing the basic cavity, that has a pressure on the surface. So that can make an erosion on the surface. And the pressure, collapsing pressure is big, and then sound is also coming. Big sound is coming. It also can come with a pump, so that the blade is eroded like this because of the cavitation. Supercritic. Yes.
Snap, crackle, pop, boom! That is the sound of cavitation destroying your propeller. That might sound overly dramatic, but cavitation poses a major danger to propellers. Collapsing cavitation bubbles release tiny bolts of extremely violent energy. That energy means death for your expensive propeller. So today we discuss the best solution to cavitation. Avoid it. How does this mystery of disaster work? Well, cavitation occurs when small air bubbles form against a propeller blade. See, the bubbles form because the water actually boils. We know that the boiling temperature of water will change depending on the pressure. Take a pot of water to the top of a mountain and it boils at a lower temperature than it did at sea level, all because that pressure is lower. Propellers, incidentally, lower that water pressure intentionally. They do this to generate lift. Catch is, lower the water pressure too much and the water can boil at ocean temperatures. It'll create thousands of tiny little air bubbles that form against the surface of the propeller blade. But these bubbles don't last very long, and when they collapse, it works like a tiny explosion against the propeller blade. If your propeller has major cavitation, it has to endure the equivalent of thousands of tiny micromines exploding every minute of its life. So cavitation is bad, and it arises from large changes in pressure at the propeller. But a propeller does not create a single uniform pressure field. The pressure varies along the propeller blades and the root due to many interacting parts of the propeller geometry. For this reason, we classify the different types of cavitation based upon the section of the propeller blade. Small amounts of sheet cavitation are acceptable. This would be only about 5 to 10% of the blade area when I say it's unavoidable. The propeller simply must pack a high thrust into a small area. These special like any other natural disaster. If you understand it, you can avoid it. Careful propeller design limits cavitation to only minor levels of sheet cavitation. Armed with this video, you will now be able to recognize the various signs of cavitation.
I'm not sure the supercavitating experimental. For supercavitating, only for the expectation. Right. We need to change the title. So skin propeller again, fixed pitch, control rotating, and supercavitating. It is for military, but it is cost. And control rotating, fuel saving, and this is a consent. Other proposed device, there's a paddle wheel, the old time, air propeller, cycloidal, voice Schneider, and Magno hydrodynamic. Let's see. There's the videos. That's for you. Here's time. Yes, sir. There's a voice Schneider propeller. It's not interesting. you see that the angle of attack is changed through using the overhead and stun, stubborn and both sides. So they are saying there is no need to have a steering. It also has a steering function inside the position. Yes, thrust and motion is changing in this. And magnet hydrodynamic is saying motion electrically conducting fluid in the magnetic field. We are using a Lorentz force law. Salt water has a gas ions, so that you can apply it by applying electrical current and make the electricity. So there's also video. And there's a real work of this kind of superconductive magnet hydro and MHD propulsion. Still, I guess it is still on experimental stage, not yet for commercial application. Many experts are saying there's a future in universe technology. And what is this? Oh, there is nothing. More video to show you how the water is pumping out through the magnetic field right there. Current is moving because of the magnetic field. Yeah. So, yes, like this. We may see one more video then. Which one you want to see? Gather wheel, air propeller. Is it? Cycle. Okay, we're gonna find it. Inside. Okay. Yeah, sometimes they use air cushion in the butt. Or like shallow water and also shallow grass. Mississippi is for today. Very well, then we can question. No. We go to discussion session. Right?
Guys, my name is Young Kim. Today I'm going to lead the discussion session, and it's about the model test. So here are the contents. So we'll start with a quick recap of the class, and then quiz, and then we'll discuss about 2 topics. So a quick recap, what we studied about model test. The model test was used commercially since William Ford's success. And that is based on Ford's hypothesis that the total resistance is the sum of residual resistance and frictional resistance. So for residual resistance, Ford's similitude can be used, but for frictional resistance, Reynolds similitude does not fit. So people have come up with an empirical formula that fits. And below you can see the formula. And this is how you can calculate the resistance of a ship based on the model test. So if anyone wants to try it, you can see this on my Patreon. So I'll have 3 questions, and question number 1 is, what is William Ford's accomplishment in the field of model-based empirics? Does anyone want to answer?
He invented dimensional analysis.
Yes, he applied dimensional analysis to model tests, right? Yes. Can I get your what is your name?
승기호.
Hey, yes. William Ford has adopted the concept of dimensional analysis and came up with some non-dimensional numbers such as Ford's number and applied it to model tests so that we can easily estimate the resistance of a real ship without building one, and by doing a test with a smaller version. Okay, then question 2 is, what is the physical meaning of Ford's number? Which is below the question. So there's a ratio between something and something at a free surface fluid flow. Does anyone know the answer?
It's the ratio between inertial force and gravity force and the free surface fluid.
Yes, that's right. So on the top, it's V stands for average velocity of a fluid, and on the below, G is gravitational acceleration, and L is the characteristic length of the fluid. And question 3 is, what is the physical meaning of Reynolds number?
There's schools.
Yes, that's right. What is your name? Okay, thanks for answering the questions. Yes. So Ford number is the ratio between the inertial force and gravitational force at a free surface fluid flow. And for the Reynolds number, it is the ratio between the inertial force and the viscous force of the fluid. So those are quiz that I prepared, and we'll move on to the main section, which is the discussion. So let's talk about the pros and cons of model tests. You can say either pro or con or both. What you want to do. Anyone have any ideas? Yeah.
Time consuming.
Yes. Yes, that's right. It's time efficient and also cost efficient because we don't have to build the big, large ships. And okay, anyone have other things that?
What I got in mind is that we can there's 2 non-dimensional variables. Yeah, they don't by a full number, but we cannot match the 2 numbers in one model.
Yes, that is also correct. That's one of the things that I said. So based on Freud's hypothesis, to calculate the frictional force, Reynolds number cannot be actually used. So we use an empirical function, but ITTC has come up with other methods to estimate the total resistance of real ships more accurately. So yes, that is also one thing. Thanks for answering. Can I get your name?
Yeah, I'll give some.
Thanks. And any more? Does anyone want to say anything about it? Someone? Okay. So I prepared some possible answers. So for pros, the accuracy of prediction. So model tests, because people have developed like very good methods to have accurate predictions. We can actually estimate the resistance of a real ship quite accurately by like adjusting a lot of stuff. So for basins like towing tanks, we can also have wave makers and stuff like that to make the condition more similar to the actual sea. And of course, it is cost effective. That is one of the main reasons why people came up with a model test. So we don't have to build the real ship before we get to test anything. And if there's something wrong with the test, we can just build another model, which is not that expensive compared to building a real ship. So it's very cost effective. And design optimization, it's like if you do a test, you can optimize the design afterwards with the results, and safety and risk reduction also relates with design optimization, but also if you want to test with real ships, that is not like approved. People need to be on the ship, which is kind of risky, and regulatory compliance. This is also like pre-testing before actual operation. And for the cons, although I said it's kind of accurate, the scale effect and every like other thing, it's not a real ship, so there will be some differences in the results. And I said it's relatively cheaper, but also it is not that cheap because we have to have a tank and we have to like try to make the model as precise as possible. So it is fairly expensive and time consuming also. And the test environment can be different. And for towing tanks, it's normally just the calm sea, or if we have wave makers, we can make some regular waves, but compared to the real ocean environment, it is different. And the complexity in data interpretation is also a problem because we cannot get the exact data from all the stuff that measurement that we have. And our last topic is, what do you think is the difference with model basins and real ship operating conditions? So it's one of the things I said. So we perform tests at a tank, but actual ships operate in the sea, oceans. What do you think the difference can be between those two environments? It can have some very simple answers. Yes.
As you said, the waves can be way more irregular.
Yes, that is also an answer. That's true. Yes. Thanks, guys. What's your name?
Waves.
Waves can be different.
Like natural factor, like landmass you didn't think about, ship crashing into it, just random, unpredictable factors.
That is also true. Thanks. Can I get your name?
Lloyd Anthony.
That is also true. So, the sea conditions is far more unpredictable compared to the text. Have one more. One. That's horse head. Yeah, we can also control like winds, but yeah. So there's kind of unpredictable weather, typhoons, hurricanes, winds, high tides, and all those like bad weather things can also affect the resistance of a ship to extreme conditions. Thanks, Francis. Yes, so these are the things that I came up with. Most of them are just normal engineering problems, but and as some of you said, wave making also different and extreme weather can be different. But also one thing is the shallow depth of the basin, because while a ship operates in the sea, the ocean bottom is far below the bottom of the ship. So the effects of the bottom, the ocean is like negligible. It's considered infinite, but at the tank, the depth of the tank is very finite. It's not that deep. So the shallow depth of the tank can affect immersion of the nodal. Okay, do you have any questions about today's discussion? If there's not, this is all I prepared today. Thanks for attending.
Okay, just 공유해주세요. 네. Alright, that's all today. No question? See you next week.